Hey guys, so we're going to look at topic 2.2, intramolecular force and potential energy. This should not take very long at all, okay? Let me share my screen here. Share, go like this, screen mirroring, MacBook, go. Okay, so here we do. We've got topic 2.2, intramolecular force and potential energy. Some of this stuff, as I said, it requires knowing things that we haven't quite learned yet. So you just kind of have to take them for face value. Okay. We are representing the relationship between potential energy and distance between atoms based on factors that influence the interaction strength. Our main concern is going to be looking and understanding a graph of potential energy versus the distance between atoms. These graphs we're going to see illustrate both the equilibrium bond length, where we have the lowest potential energy, and the bond energy. So we'll be looking at bond length and bond energy. Bond length and bond energy. Bond length, bond energy. It took me a while to do that. We'll see that the bond length is influenced by several things. The size of the atom and the bond order within which the atom is bonded to another covalently bonded. Higher orders are shorter, and we'll get into that. And then we'll look a little bit at something I've already bled into of ionic compounds and Coulomb's law. Okay, so when we talk about these graphs, which you see is coming up in the next slide, this is a potential energy versus the distance graph, okay? They always look something like this. Now, let's look at what's going on here. This is your potential energy, okay? Notice the most stable state is the state with the lowest potential energy, okay? And so this, how far down you are, is going to relate to your bond energy, okay? Further down has a greater bond energy. That means the bond is stronger. It takes more energy to break it. Further up would be a smaller bond energy, okay? Now, when I say further up, I mean compared to here, to here, to here, okay? The further down this hill or this dip goes, the greater the bond energy. Let me clean up my screen a little bit, okay? So the further down that dip goes right there, the greater those bond energies are. Now, we're going to see that a triple bond, we haven't learned to draw them yet, that's a triple bond, is stronger than a double bond, is stronger than a single bond, okay? The bond order, if it is a triple bond, look how easy this is. It's a bond order of 3 versus a bond order of 2 for double bonds versus a bond order of 1 for single bonds. So the higher the bond order, the stronger the bond, the lower the potential energy. Okay? And what I'm going to get, the other part of my graph has how far across the dip hits the x-axis, right? So for this one, let's get a yellow. We see that the dip hits here. We could imagine it hits here or it hits here, okay? So here we're talking about how far down. Now we are talking about how far over that it crosses the x-axis, okay? how far over it crosses the x-axis, and that is going to give us a bond length. Okay? And I also know that a triple and a bond order of 3 is shorter than a bond order of 2, and a bond order of 1 is longer. So remember, the shorter here, the closer the proximity, the stronger the attraction, right? The longer, the further the proximity, the weaker the attraction. Now, here, we would expect to see triple bonds furthest to the y-axis, or very small atoms sharing electrons so that they get very close to each other. Over here, right, it would kind of go in order. We'd be looking for double bonds, and then we would be looking for single bonds or larger atoms that cannot get as close to each other, okay? And that is your potential energy diagram. And over here, it's telling you what I've been telling you, okay? This bond energy would be equivalent to this right here. And the ideal bond length, the distance between the radii would be 74 picometers, really small. I think that goes to the -12th of a meter. Okay. Here we have them being too close together over here, right? And they would be repelling. Over here, they're so far apart that there's no longer any attraction there. Okay. Same deal, right? This is relative of the distance. This gives me the bond energy. Distance, ideal bond energy. Bond and the bond length, okay? Okay. All right. The smaller the bond, the more smaller, shorter. I'm going to say shorter is a better word there. More energy required to break it. Smaller atoms, closer together. All right, you want to remember that too. Closer the proximity, the greater the attraction. And then we would compare single, double, or triple. It's note pointing out that halogens always form single bonds, right? Br, Br, Cl, Cl, F, F, I. You just know I2, Cl2, your diatomic molecules. No, the halogen diatomic molecules. Double bonds, O2 is double. You may as well memorize it. And then your triple bond is going to be your nitrogen, diatomic nitrogen. Your HI would be over here. A lot of times with these bond energy, these graphs, they include these diatomic molecules, and you have to identify who would be who. Okay. This is the same thing. Bond strength increases from a single to a double to a triple. Bond length decreases. We get smaller together when we have a triple bond. It makes sense, right? There's more things pulling it together. Okay, let's look at let's apply this. This is the Cl-Cl bond here, right on the graph. We are to predict about the bromine bonds in terms of bond length. Well, Br is larger than Cl, right? And I know that because of periodic trends. So that means the bond length should be larger. It should be larger, which means that instead of the length being here, we should probably, you know, I'm just going to put it here, somewhere to the right of the the ClCl, right? We said this is ClCl here. And the bond energy. Well, if the bond length is larger, the bond energy should be lower, right? And that's going to give me maybe around here, right? Maybe something around here for the bottom of my dip. So I'll go ahead and just see how this works. And I'll kind of go like that. And I would bring that right up to the 0 line there. Okay. So I'm just going to erase that. There we go. Bring that right up to the 0 line. And we just had to predict. But those would be the two items one would look for in accurately grading, judging your prediction, is to see that this is in fact over and this is in fact up due to these ideas here. Okay. This is upside down. I noticed that a little while ago. Not going to worry about it, but I'll go into the main PowerPoint one day and fix it, but I'm not going to worry about it right now. The question is asking me to determine the relative ionization energies of magnesium oxide, potassium chloride to sodium fluoride. So I'm just going to say, would it be higher than 930 or lower than 930? Okay. And what I'm going to notice, and of course they're going to give you elements you can work with. I know that Na, I'm going to look at all of my metals, is here, potassium is here, and Mg is here. Okay, now I'm going to look at my non-metals. Oh, goodness gracious. Take me back. Now I'm going to look at my non-metals. I've got F, Cl, and O. Okay, remember these are ions, right? They are ions. So I need to be considering the ions here. The charges, right? So we know -1, 2 negative. It should be 2 negative, guys. 2 plus, 1 plus, 1 plus. So let me just fix that since I'm the instructor. And I really don't need that 1 there, do I? Okay, well, Na, right? Let's look at this guy here. Magnesium has a greater charge than Na, right? So that makes Coulomb's law. It increases that Coulombic attraction. And magnesium is smaller than Na, right? So in terms of the magnesium and the sodium, magnesium is setting up to have a greater Coulombic attraction. When I go to look at oxygen, I see that oxygen has a negative charge. He is a little bit bigger, but because of these large charges, and he is a little bit bigger than fluoride, but probably not too much, I'm going to say that his would be higher. I'm going to say that his would be higher than this. Now, let's analyze the next one in maybe a blue color. I'm going to compare these two, right? The two there. And I'm not going to worry about this Mg. I'm going to look at potassium versus sodium. And he is bigger. And the charge is the same. Because he's bigger, he's further apart. I'm going to compare the chloride to the fluoride. He's bigger. So I'm going to say his lattice energy would be less because the larger cation and the larger anion are going to make this crystal lattice structure. They will be further apart, right? The crystal, each individual charges, and that's going to make them weaker than in that attraction between the sodium and the fluorine. So that would be my prediction there. What is the ideal bond length between these atoms according to the graph? Actually, that's the bond energy. This is the bond length. Okay, so that would be the ideal bond length. For which of the following ions is the energy required to separate the ions the largest? Well, I'm immediately going right here because I know that they're in the same period. So they're going to be very similar in sizes, and the charges are the greatest. Okay. And then I would go here. And then I'm really questioning myself. I would go here. And then I would go here. Where I'm cheating real quick. I'm looking at BE. Yeah. I'm going to stick with it, guys. I'm going to stick with it. I'm going to stick with 1, 2, 3, 4. I'm actually going to check and make sure I'm right. What can be said, if I'm wrong, I'll tell you in class, okay? What can be said about the melting point of BeO compared to the melting point of lithium fluoride? Well, I would imagine that if this has a stronger crystal lattice, it's going to be harder to melt that substance and separate those ions so that they can start to roam a little bit. And I would think that this would have the higher boiling point. Now, if I was wrong right here between lithium and fluoride and beryllium and oxide, and I'm feeling pretty good about my prediction, but I am going to look it up, then I would be wrong right here. The answer would be the lithium. Which of the following would have the greatest bond length? That means furthest apart. Okay. And greatest bond strength means closest. Well, remember, nitrogen, we know, has triple bonds. Chlorine is a halogen. They all have the single bonds. Oxygen tends to form double bonds, and it does here. I need to put my electrons out here. We'll learn how to do that later. If you don't remember, we will definitely review it. I put my electrons because you have to put your electrons. So greatest bond length, that's going to be the Cl2. Yeah, because it's got the single bonds and the largest atom. This is going to be the greatest bond strength because of that triple bond. Okay. Ions don't matter here because there are no ions here, right? These are covalently bonded. No one's transferring electrons. To use the word ion when talking about anything in number 3 is wrong. There are no ions. They are atoms sharing their electrons. No giving, no taking, no cations, no anions. Okay. That's it. Okay. Figure out what your questions are. Bring them to class. I'm going to check on that BeO. All right. Stop share. And